Hey guys, BuildZoid here, and today we're going to be taking a look at an RTX 3090 that tried and failed to run Amazon's New World MMO. So this right here is a Gigabyte RTX 3090 Vision. It was sent to me by its owner because, well, he tried to play Amazon's New World MMO. The card promptly turned off and then never turned on again. And because he bought it secondhand on eBay, Gigabyte basically rejected his RMA request. And so, yeah, he decided, I went to, and basically I made a post on Twitter asking if anybody has a card that they'd be willing to loan to me so we could figure out what is it that's actually dying on the 3090s, because, it's all well and good to know, yeah, 3090s die playing this game, but I want to know why they die. Like, what part of the 3090 is New World killing? And so that's what we're going to try to do today. Well, I've already figured out what part it is, but yeah, we're going to take a look at that. And before we get into that, a little bit about the card. So this is an RTX 3090 Vision from Gigabyte, and it is actually pretty custom. More like at a first glance, I thought it was reference, but on closer inspection, it became very obvious it is very not reference. So yeah, I mean, the obvious things are sort of like, oh, you got these power connectors, but these are power connectors. Those don't really matter in the grand scheme of things. No, what we have as major differences here is we've got memory power over here. We've got a memory phase over here. We've got 3 phases of MSVDD above that. This is normal. This is like reference style. And then above that, we've got 1, 2, 3, 4, 5, 6 power stages of VCore. This is not standard. Normally, you would expect to only see, I think, 4 of them in this area, and here we have 6 of them. So yeah, we've got 6 VCore power, and I'm saying power stages, or well, like power channels, because the thing is, the voltage controller on this card is a UP9512, and there's more power stages and inductors than there are phases on a 9512. So Gigabyte has to be putting some of the power stages in parallel, and therefore it is incorrect to say that these are all 6 separate phases, because I don't know that. I've not checked that they run out of phase with each other. But anyway, so we've got 6 power stages and inductors over here on the other side, and then we have a memory phase over here. This is pretty normal. We've got another memory phase over here. Then we've got VCore, 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 memory, and then 2 more phases of MSVDD. And so MSVDD is a 5-phase. That's standard reference RTX 3090 stuff right there. But we've got 10 power stages for the VCore VRM. And also Gigabyte upgraded the power stages from 55 amp DRMOS components from Alpha and Omega Semiconductor to 60 amp DRMOS components from Alpha and Omega Semiconductor. So yeah, this is basically, like, on paper, this is a slightly upgraded RTX 3090 PCB. For the capacitor configuration, we've also got some upgrades. Like, we have a few capacitors that most manufacturers don't bother populating, like this middle one that is present. We've got 470 microfarad polymers instead of the NVIDIA spec, which is 220s. So we've got more capacitance behind the core. We've got some optional capacitor pads that Gigabyte didn't bother with. And yeah, all around, like, at a glance, this really just seems like a slightly upgraded RTX 3090 PCB, and it's a bit confusing that it would fail because, it's not the absolute bare minimum of the specification. The voltage controllers are, as I mentioned earlier, at 9512 for the VCore. We've got a 9512 for the MSVDD, and then there's a 9511 for the memory rail, and that makes sense because the memory rail normally just sits at 1 voltage all day, so you don't really need a more advanced voltage controller for that, like the 9512s that we see for VCore and MSVDD. So yeah, the only thing that I find suspicious about this card in this scenario is the fact that we do have more power stages than we have phases on the controller, and I still haven't actually had a chance to measure how the VRM handles that. But anyway, that's sort of what we have in terms of GPU setup, right? Like, it's 2 8-pin power connectors with these weird extension connectors, and then we have some power from the PCIe slot. So let's get to some probing. And luckily for us, Gigabyte included a bunch of board protection fuses, and I call them board protection fuses because they're not there to protect your power supply. They will they're not supposed to do that. Like, that's not their job. Your power supply is supposed to have its own protections built in. And they're also not there to prevent the card from failing. What these fuses do is when you have a catastrophic power stage failure, they prevent that failed power stage from just pulling in way too much power and destroying everything on the card. or more like destroying the PCB of the card, which is actually very common on, say, 980 Ti's. It's not too uncommon to basically have the bottom two power stages burn out, and when they burn out, well, they burn the surrounding area of the PCB to charcoal, and then you've got like some serious, problems to deal with when trying to fix the card. Now, by including fuses, the GPU, like the fuse basically limits how much energy is available to the short circuit when it occurs, which means you don't get that, massive amount of heat damage that you get when you have cards with no fuses. So yeah, good on Gigabyte for including the fuses. Let's see. Now let's check those fuses. Also, they make troubleshooting a lot easier because you just have to check if the fuses are shorted, and that'll immediately tell, or more like check which fuse blew, and that'll tell you which part of the VR, like what part of the card failed. So this fuse isn't blown. It's just my pros being there. So that fuse is nice and healthy. And if we go over here, we've got another healthy fuse, right? Very low resistance. And then we get to this fuse over here, and this fuse, oh, come on, turn back on. Oh, nope. Nope. There, this mode. Yeah, so that fuse has 4.7 kilo ohms of resistance. So that one is blown. That one is very much blown, but there's no visible damage on the card anywhere. Like, you can't even tell that anything is wrong with the card. But you definitely do not want to just replace that fuse. If you replace that fuse, you're going to have a very bad day. Actually, your power supply will probably stop you from turning the system on, but if your power supply is crap, you're going to have a really bad day. So let's check why that fuse is blown. So we're going to grab our ground off of the PCIe slot bracket, and we check this fuse, and we can see that the resistance is going up and up and up and up on this side. On the other side of that fuse, we find the same behavior, the resistance going up and up and up and up. And that's normal because on the 12-volt power planes, we have a bunch of capacitance, and so you're not going to get like a steady resistance measurement a lot of the time. But yeah, there's nothing really wrong with that. And we know there's nothing, like if there was something wrong, that fuse should have blown. So we don't have to worry about that too much. If we check this fuse over here, we have extremely high resistance, which is completely normal. That's not like a contact problem. That's actually completely normal. That's what you'd expect. I mean, some cards will measure like hundreds of kilo ohms, but yeah, on both sides of this fuse, we get like a fraction of hundreds of kilo ohms again. So that fuse is obviously fine, and that's why it didn't blow. Like that fuse isn't preventing anything like that. It's fine. Which is also why it's not blown. But if we check the blown fuse, so from this side to ground, we get 4.7 kilo ohms, which is the resistance of the fuse itself. And if we measure from the other side of the fuse, the side of the fuse which is actually connected to the V-core VRM, yeah, yep, that's no good. So that is 0.15 ohms. Which, conveniently enough, is roughly the same resistance as what you get if you measure the V-core to ground. Assuming that I don't have contact issues. Now, this is a very normal like the core of a GPU like this is a huge chunk of silicon. A very low resistance, like 0.112 ohms, that's completely normal. That's in line with what that's what you'd expect to measure on a card like this. So the cores, like, there's no short circuit on the V-core, okay? Like, that is not a V-core short circuit. That is 12 volts shorted out. Like, potentially 12 volts shorted into the V-core rail, or 12 volts shorted to ground, and if we try to measure... actually, if it was 12 volts shorted to ground, we probably wouldn't see the resistance being almost the same as V-core. But, yeah, like, the core's not shorted. The VRM is. And we can see that here. Because if we check, say, MSVDD... which is also a very low resistance rail. Well, let's check memory first so that you can see like a more normal power rail. So memory is, approaching 40 ohms of resistance, and that's normal for the memory rail on a 3090. And if you check the MSVDD, we have about twice as much resistance as we have on core, which is what you'd expect. It's a lower power rail. There's less silicon connecting that rail to ground, so it makes sense. But yeah, so we have a short circuit on probably the V-core portion of the VRM and connected to this 8-pin power connector. So, we're going to flip the card over, and now we're going to try figure out which specific power stages are connected, which group of power stages is blown up. Because the thing is, from the V-core side, like all of these power stages are in parallel with each other. Inductors have basically no resistance to them. So if you measure through an inductor like this, because an inductor is basically a very fancy piece of wire. And if I could get contact on the probes to work. Oh, the multimeter decided to stop being cooperative again. Sometimes does that, which is really annoying, because that's like an expensive keysight meter, and yet very frequently... Could I... Yeah, unfortunately getting measurements off of inductors just doesn't tend to go very well. There we go. Yeah, so measuring through an inductor, just... They're very low resistance. It's basically a fancy piece of wire. And because of that, all of the power stages are in parallel with each other. So if you're thinking of like going, oh, I'm going to like check each phase, doesn't work. It's never going to work. They're all in parallel. You can give up. So what actually we're going to do is we're going to be checking the 12-volt input filtering capacitors right behind the power stages, because by identifying which of these capacitors are shorted out, we get a rough idea of which power stages could be shorted out. And by input filtering caps, I mean this, like this cap over here, this cap over here, that cap, this 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 cap. Actually, you couldn't see the last one, but yeah. These caps, and we're just going to be checking those. We're going to check them directly there because I don't know which side of those caps is ground and which side is 12 volts, and I don't really care to figure that out. And then we're going to do the same thing on the other side of the VRM because I don't actually know what the 12-volt power distribution on one of these cards looks like because I don't have schematics. Which would certainly make this a lot easier, you know, if you had schematics and you just went like, okay, well, this fuse blew, and then you could go and check all of the power stages that are connected to that fuse, and like you'd be done. You could literally skip this part of the process that we're going to go through, but yeah, for one reason or another, you can't get schematics for motherboards or GPUs or, well, anything. So yeah, let's get to this. So we're going to start with that. Man, I've managed to entangle my probes. So I'm just going to unentangle them for a bit, and then we're going to start with that cap over there. I was having real issues with getting the contact right. So that one just sees, yeah, resistance rising, so that one's fine. Check this one over here. That one's fine. Check this one over here. And if I could get the probe to stay where it's supposed to be. Not fine. Yeah, very not fine. So we're going to mark that one. Because I'm not going to remember it otherwise. I'm just going to check that it is the same one, because... Yep. So, actually, I wasn't paying attention to what I was looking at. So, I'll take that one. Damn it. There. Just put a dot. And let's check another one. This one should also be shorted. Like, I went through this before. So, yeah, that one's also shorted. Oh, come on. I mean, it's just the next one in line, so we're going to put a dot near it. This one. That one's fine. Yep, the resistance just goes up and up and up. This one. Fine. This one. Fine. And fine. Come on. Also, yeah, that one's probably connected to the PCIe slot, and this one... Fine. Okay, so that's this side of the card checked. Now we're going to go over to the other side. We don't need to check the memory, because if we go from, if we go from the memory power rail to the blown up fuse, we just see memory resistance. So, like, that measurement is telling us that we're measuring memory through the memory chips to ground, and then through ground to probably through the failed power, like through ground, probably through V-core, through the failed power stage, and to this fuse. So we don't have to worry about any of the memory phases, because all of the memory phases are, like, they're all fine. We don't have a memory failure, memory power failure, so you don't need to bother checking the input capacitors for the memory. We're going to check this. This is a memory cap, and isn't it? Yeah, that one's memory, right? Yeah, so that one's in line with some of the shorted out ones. Actually, that would be kind of whack if... Maybe it is the memory that failed. Let's check this one. Okay, that one's shorted as well. Because they're, like, normally when you have a power stage fail, it shorts the power stage to the output. But if it shorted the... Actually, well, if it somehow managed to short 12 volts just to ground without interacting with the power rail, I still think it's V-core. But that is something, like, it is worth keeping in mind. So I'm just going to note that. But I really don't think I'll have to actually deal with the memory. Like, if we had a short circuit from 12 volts to memory, then I'd say, yeah, we need to do something about the memory power stages. But currently, like, the thing is, this is just telling us that those memory power stages get power from the same place that all of the V-core power stages are getting it from. Yeah, that one's shorted as well, isn't it? Oh. And we're going to check this one. The thing, like, in my experience, power stages fail high side. Like, they don't fail the low... Like, the low side doesn't really tend to fail very often. That one's also shorted. Because, of course, it is. Pretty sure most of this side of the card is shorted out. And this one. Also shorted. Up. And if we check this one's fine. Yeah, these probably run off of the PCIe slot, don't they? Fine, and fine, and this bottom memory one. Actually, no, this one's MSVDD, isn't it? Yeah, that one's all... Actually, that one's... Wait a minute. What are you? Oh, right, that's MSVDD. Ooh, fun. So this bottom one... Not fine. Why would you... Man, NVIDIA cards and their 12-volt power distribution is something I will never understand. Like, why would you... Just split the power connectors half-half between your power phases, between your phases. Why make the card so complicated? But yeah, okay. So I still suspect V-core more so than I suspect anything else, but it is worth noting that MSVDD, and the reason I suspect V-core so much is just the resistance is so low. Like MSVDD, right? If we check MSVDD to ground, is relatively high resistance. It's more resistance than the core is, right? Like that's 0.3 ohms right now. Also, the resistance of the GPU core actually goes up and down based on how cold it is, which gives me an idea. I do still have some liquid nitrogen. We could try cool the card a bit, and see if we can bring up the core resistance so that we get a better idea of what's short. Yeah, that might work. So I think I'll test that off screen, but yeah, so far, so basically what we can say right now for 3090s is just like, well, some part of the VRM fails. It's probably V-core based on the fact that if I measure from that blown fuse to ground, we get what looks like V-core resistance, right? Because if I check the V-core phases, we get a similar resistance to what we get on that shorted out fuse, assuming that the probe stops having contact issues. You know, I put quite a bit of effort into trying to clean the card so I could not have to deal with the fact that there's junk all over the pads, but yeah. Whereas if you check MSVDD, like it's still low resistance, but it's like twice as much as what we get on V-core, so I don't really think... Yeah. Like, that's basically twice as much as what we get on V-core, so I really think, like, that would show up on the fuse, I think. So I really think the V-core VRM failed, and the repair would be to just replace the failed power stage after figuring out which one it is. So, yeah, that's it for the video. At this point, like, the issue with having just one of these cards for this kind of failure is I don't know if it's always the V-Core VRM that fails. I don't know if it's always the same power stage or same set of power stages on the card that fail, right? Like you'd have to have more than one card. Like having one card and going like, okay, well the V-Core VRM failed, which I'm 99% sure is what happened here. Like that doesn't tell us if that's a design flaw with the V-Core VRM itself, or if it's a, like, because we have options, like the V-Core VRM is too small, and therefore cards like this and cards like the reference cards would die playing New World. Because this should technically be more powerful than a reference card, since it has more power stages on V-Core than a reference card. However, it could also be that because this has an asymmetrical VRM, the way this VRM operates is bad, right? Because it's asymmetrical, and so the controller isn't doing a good job of dealing with the fact that there are 10 power stages connected to 8 phases, which, if that sounds like insanity to you, join the club. No motherboard vendor voluntarily does this to their motherboard. Nobody does this on motherboards. Instead of, alternative, what you could do is run this as a 5-phase, and that shouldn't have any weirdness to it. But I have a suspicion that NVIDIA is so obsessed with current balancing that they wouldn't allow the manufacturers to just build it as a 5-phase. So, yeah. But basically, so the options are, one, the V-Core is just completely inadequate in terms of overall power handling capability, which would mean all 3090s are susceptible to this, or at least all 3090s based on the reference design are susceptible to this, or actually reference cards would be more susceptible to this because this should be more powerful. 2, it's a design flaw in the current balancing of the VRM due to the fact that the phases aren't symmetrical. If that's the case, then that's just like no more asymmetrical VRM designs. Thank you very much. 2, dodgy overcurrent protection, but that I feel like would still be tied to the asymmetrical VRM design. Because if you have an asymmetrical VRM, I'm really not sure how you're supposed to implement overcurrent protection on this, because your overcurrent protection should be, like, as far as I know, most controllers set the overcurrent level for the whole VRM at the same time. So each phase, like, you can tell, hey, all of the phases have an 80 amp current limit or a 50 amp current limit. But if you have 2 phases that are supposed to have twice the current limit, then you'd probably end up setting the current limit for the whole VRM to the OCP of the 2 most powerful your most powerful phases. And it's like, but what if one of the weaker phases gets overloaded? The controller's not going to stop that. So yeah, anyway, I'm going to try fix this card. Yeah, I'm unfortunately, this doesn't answer the question of, like, why do these cards fail? Because, like, if this was a nice symmetrical VRM, I'd just say, okay, this is grossly inadequate in terms of power delivery requirements for New World, and NVIDIA should probably set some kind of, like, power limit specifically for New World. But this is not symmetrical. Right, we've got 10 power stages on 8 phases, so... Or I'm assuming it's on 8 phases. If it's 10 power stages on 5 phases, then we go back to, like, it becomes a symmetrical VRM, and then it's like, okay, then it's evidently not powerful enough. But I'm not sure about that. Actually, there is a way to check, with a lot of really annoying probing, to see, like, how the phases are distributed between the... Actually, you know what? I think maybe there's a chance I could get schematics for this card. Maybe. I seem to think, like, I seem to remember seeing a leak of a whole lot of GPU schematics recently. Maybe this was among them, and that would make it, because the thing is, like, you'd have to, I don't feel like checking the current sense configuration. Well, yeah, yeah, so unfortunately, I don't have a verdict on what's failing on these cards. The thing is, it is worth noting that, like, the FTW3s, which were the first cards reported as failing, those were all, like, those are asymmetrical, very asymmetrical. They have an 8-phase controller driving a 13 power stage VRM, if I remember correctly. Like, that, like, when you build a 13 power stage VRM, it's like, okay, we are making our lives difficult. Like, we are intentionally making this as complicated as possible. But I also saw somebody report like a Strix failing trying to play New World. That's also an asymmetrical VRM though. I think that's like 10 really high-end power stages with a really high-end controller, but it's still not a symmetrical VRM. So, yeah, it could just be like a fundamental problem with, hey, if you build your VRM asymmetrically, it doesn't work. In like worst case scenario becomes a very real problem. Yeah, I'm not sure about that because this is a one-off, and if it was consistent that it's always like if it's always this fuse that's blowing, then that sort of points to there being probably an issue with the fact that the VRM is not symmetrical, and therefore like an issue with the current balancing, which again is just tied to the fact that you don't have symmetrical phases. Because the controller, like if you're trying to current balance an asymmetrical VRM, I can't imagine it being very easy compared to what controllers are normally meant to do, which is just evenly distribute the current between all of the phases to the best of their ability. Which I don't know how, like with a VRM where your phases aren't all the same size, you need to preferentially put more load on like whichever phases are bigger. And the controller probably isn't thrilled about having to do that. So yeah. I wish I had more conclusive information here, but yeah, like the thing is I also saw a Zotac card burn up, but that might have also been slightly customized. Because the thing is, like, I'd love to know if anybody's had a reference, like, proper reference card die. Or if it's only been affecting cards which have a few too many power stages relative to how many phases they have. Because, yeah, so far, it's, like, yeah. Anyway, and also it's worth noting that GPUs generally have really high failure rates compared to everything else in a system. So there's going to be some cards that just fail because they snuck past the quality assurance checks at the factory. But yeah, anyway, that's it for the video. So big thank you to the person who decided to loan this card to me. Because, yeah, I mean, I was really interested to find out what fails on these. And I was honestly expecting it to be something like the memory controller, like the MSVDD rail failing. But apparently it's just vCore, which is like the most normal failure for high-end NVIDIA GPUs ever. Because GPUs that blow up vCore are 980 Ti's, 780 Ti's, 780s, Titans, Titan X Maxwells, 1080s, 1070s, GTX 590s. What else is like basically any high power draw NVIDIA GPU ever made. If the vCore VRM doesn't have a tendency to die, it's weird. So, yeah. So this is really anticlimactic for me in from that perspective of like, oh, it's just vCore. Because it's always vCore with NVIDIA cards. But yeah. That's it for the video. So thank you to the person who decided to send the card over. I'll see if I can get it fixed for him. Yeah, that's it for the video. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch. Both Patreon and Teespring help out immensely with running the channel, so it would be much appreciated if you check them out. And that's it for the video, so thank you for watching, and goodbye.